So before we start getting too far into our topic about structure and bonding, we're going to make sure that we actually have a good understanding of atomic structure at the level where we're expected to know up to the end of level 2. And to be honest, it's really just the Bohr model of the atom, which is way back from 1912 or somewhere around then. However, an understanding of the Bohr model, which really only works up to calcium, so number 20, is actually good enough for what we're about to do on atomic radius and ionic radius. Okay, the same principles can be applied, and as you learn more about transition metals and so on, you can still apply the same rules. So the Bohr model was one that took the Rutherford model one step further and explained that electrons can be found at different energy levels or on different shells, and that's what basically stopped them crashing into the nucleus when they repelled each other and so on. Still didn't work perfectly for explaining everything, but it was a step better than the Rutherford model. So over the last few years, you've been taught that the atom is made up of a nucleus, very dense nucleus. This is nowhere nearly to scale. At this scale, you would not even see the nucleus or the particles inside it. And then the electrons are in shells around that. We're going to take that word shell and get rid of it now. We're going to call them energy levels. Okay? So the first energy level fills, then the second, then the third, and so on. The reason we're going to call them energy levels is it'll help us understand this very simplified quantum mechanic model we're about to get to. But for today, just the Bohr model. Okay, so the first thing is the nucleus, which we can find in the middle here. And, I haven't given charges or anything there, but what two particles do we find in the nucleus?
Protons and neutrons.
Great, so we've got protons, and let's say another red ones.
Yeah.
And we've got neutrons, which let's say for argument's sake are the green ones. Use green because green's normally the neutral colour in an indicator. Sort of give you the idea that there's no charge in those. When I look at atomic radius and ionic radius, the neutrons actually have no effects. They don't need to be mentioned. They don't actually need to be mentioned. So you often won't have the mass number in a question as shown here. You don't have the mass number, because the neutrons are irrelevant. You don't even need to mention them in your answer. The neutrons are not relevant. The protons are though, and why is that? What is it about protons that's going to be important for how big an atom might be? They have a charge, and what is that charge?
Positive.
Cool. So these have a positive charge, which means that they're going to have an effect on what other things in...
Electrons.
Fantastic. So that, what are they going to do to electrons? Good stuff. They are going to repel other protons though within the nucleus. That's, to put it very simplistically, why neutrons are there. But they're going to attract electrons. So the bigger the atomic number, so comparing, say, chlorine to aluminium being 13 and chlorine being 17, chlorine's got more protons. So the charge of its nucleus is bigger. So it has a stronger attraction on each electron, doesn't it? Okay, so that's the first thing to consider. So the larger the nuclear charge, so the more protons it's got, so the larger the nuclear charge, more protons, the larger the attraction to each electron. So it's going to attract each electron just that little bit more for every one more proton that's in that nucleus. So if I was to look at aluminium, I'd expect it to have less pull on its electrons than chlorine does. 13 protons versus 17. Okay, so that's the first thing that we're going to consider when we look at atomic and ionic radii. How big is the nuclear charge? We're just going to underline that word there because it is such a useful word to use in our written answers and when we're describing it to each other. Right, so that's the first part. What's the other big part of the atom that's going to be very important? And we used the wrong word previous years. We're going to use a better word this year.
Energy levels.
Good, the electron energy levels. So here, We've got these energy levels. And just as we remember from last year, we put 2 in the first energy level, then if we've got a third electron, we put it here, and so on. So I've done nitrogen here, which has got, quickly, brain fade, has got 7, so hopefully I've got 7 here, 1, 2, 3, 4, 5, 6, 7. So I've got my 7 electrons there. Now, when we do electron configurations later in the unit, we'll learn about how they're arranged and what we call orbitals. So S orbitals, P orbitals, and D orbitals. But just for now, let's keep it really simple. Let's use the Bohr model. 2, 8, 8, and then we'll put 2 more in there and we'll stop at calcium because it gets complicated after that. So when you see ones in the questions that I've given you that are beyond calcium, they are going to be just a little bit harder to explain with your current knowledge, but you'll see that your answer for those will get better later in the unit. Okay, now these are, as the name suggests, made up from electrons, but they're also primarily empty space. All right, the electrons whiz around, but actually they're usually pretty much empty space. But they have electrons, and what is the charge of an electron?
Negative.
Negative. So we know that they're being attracted to the nucleus by the positive charge of the protons. Do they have an effect on anything else in this atom? Okay, I'll give you a bit of a heads up on this one. The reason why Rutherford's model didn't work, where they just had one big electron cloud, is that the electrons were going to interact with each other, changing their orbit, losing energy, therefore eventually crashing into the nucleus. Yes, it's oversimplified for those who are very good at physics, and I apologise for that. However, this means the electrons interact with each other. The reason they're on these special orbits that I'll teach you about later is so those interactions are not quite so dramatic. Okay, so they actually don't crash or jump around too much. So they're actually going to do what to each other because they're negatively charged? Good. So they're going to repel other electrons. They only actually really repel other electrons within their own energy level. There is an effect between each level though as well, but it's not a repulsion. Okay? If this has got electrons in it, so the first energy level, and the second, the effect of these 7 protons, and we're looking at nitrogen here, the effect of these 7 protons is weaker on the outer electrons than it is on the inner ones. It's like thinking about filter paper catching some of this stuff when you pour it through, or another way to think of it is having barriers in front of a magnet. So if you had 2 magnets but you put some bits of paper, or then the paper won't do much, but if you start putting some books in between them, lots of bits of paper, then you start diminishing the strength of attraction between the 2 magnets. Okay, so it's very similar to that. We call this shielding. Electrons at a lower energy level shield the effect of the nuclear charge. They make it weaker. Okay, so lower energy levels, notice I'm starting to use some summaries here. Big E for energy, little e for electron. Lower energy level electrons shield some of the nuclear charge. So the effect of the attraction here is going to be much weaker, on this electron, it's going to be much weaker than the effect of attraction on this electron. There's another thing where the magnet analogy is really good as well. If I had 2 magnets close together, it'll be harder to pull them apart, whereas if I had them here, so distance involved, then it's easier to pull them apart. And the same thing applies here. The more outermost electrons do have a weaker attraction because of their distance as well. That will become important when we do things like electronegativity and ionization energy, but not yet. Okay? What's important is that if I've got electrons here, it will weaken the attraction there, which will then allow the repulsion to become more important. Okay? So, These are the things you need to put in any discussion or justification. So let's have a look at this first question, which is from the 2011 NCEA paper. It's a standard that doesn't exist anymore, which is why I've put the number there so you can look those up yourselves at a later date. It says here, state which has the larger radius, aluminium or aluminium 3+. Justify your answer. Now if I have a think about this, just using the Bohr model, what do these two have in common? What is the same about both of them?
The number of
Protons.
The number of protons. They both have 13 protons. Okay? So both have 13 protons. That means their nuclear charge is identical. Yes? Okay. What is different about them, hence the charge, is what?
electron number.
Electron number, and therefore their electron configuration. Just using last year's style of writing it, we'd write the electron configuration of aluminium is 2, 8, 3. Okay. Aluminium ions would be 2, 8. Sorry, I've got the 3 plus there. Would be 2, 8. So without the 3. So that's completely correct. The number of electrons has changed. So the shielding by the first energy level, this one here, is going to be the same in both of them, isn't it? Because the nuclear charge is the same and there's the same number of electrons in the first energy level. At the second energy level, well, the amount of shielding would be the same if they both had them in the third energy level. This is where we see the big difference. So, knowing that each energy level is a bit further away, the easy answer for this would be that the ion would be bigger, wouldn't it? Would be smaller than the atom. The atom will be bigger because it's got electrons in the third energy level, whereas the ion does not. That makes sense, doesn't it? Just by drawing it like that, which is how we'd be expected to be able to do this if we're learning chemistry at this level. Okay? So by now you should be able to do that without much thinking. That's pretty much your answer, to be honest. That would explain it, but it wouldn't justify it. Justifying would go on to talk about the fact that they have the same nuclear charge and why. Okay? It would explain that the removal of those 3 electrons means that the outermost electrons for the ion are only found in the second energy level, whereas the outermost electrons are found in the atom are found in the third energy level, which is further away, because it has another layer of shielding. They're actually quite far away. So when you come to assign numbers, that's where you start looking at the shielding. If this was going the other way, let's say chlorine to chloride, it gets a little bit harder. This one over here. Okay, and you see the difference is huge. It's nearly doubled. This is the correct order, by the way. So these are, chlorine is 99, chloride is 181. PM, picometers. 1 times 10 to the negative 12 meters. So a millionth of a millionth of a meter. Okay, pretty tiny. A millionth of a millionth to a meter. So I'm going to write that up here. 1 picometer equals 10 to the negative 12 meters. Alright? So, in this case, why is it such a dramatic change? What's the same about them? 2 things this time, by the way, not just one. 2 things are the same about these. They're both, well, it's chlorine and chloride, so they've both got how many protons? 17. Great. There's number 17 on the periodic table. Great. So that's in common. This one is 287. This is 288. So what else is the same about them that wasn't true over here? It's got a different number of electrons, but same number.
Shells.
Great. What we did call shells, we're now going to call energy levels. Same number of energy levels. So why such a dramatic change? And it's something I haven't mentioned from that diagram on the left so far.
Is it because the level is full?
I mean, it's the fact that it's changed so that the fact that it's full is not what's important. The fact that it's changed the number of electrons in that shell or energy level is what's important.
Would it be to do with the ratio of electrons and protons?
Not
maybe?
quite. I mean, the
Is
level.
it the speed they're going around?
Not quite. I like the way we're thinking. The amount of attraction for each electron is the same because there's 17 protons. And there's the same extent of shielding because they're at the same energy level. Alright? So you've got the same amount of the same effective nuclear charge. It's the same on each electron. The fact there's another electron though affects something else. So we're saying it's got no change in nuclear charge, no change in shielding. So what have I missed?
The repulsion.
Good. If I put just one more electron in that energy level, the effect is that for that one more electron to fit, as it were, that electron energy level has to accommodate a much larger space, a much larger volume, I should say. Okay? So therefore its radius gets a lot bigger. Okay? So from an atom to an anion, the radius gets larger because of electric repulsion. That's your explanation, not your discussion. Okay? Going from an atom to a cation, it gets smaller because you have fewer energy levels. Again, that's the explanation, not the justification. All right? So your task is to write up proper justifications or discussions for those 3 questions before I see you again on Tuesday.